Proof by exhaustion then, section 7.5. And the idea of exhaustion here is that you have a number of possibilities and you exhaust them all. You go through them one at a time. So let's have a look at this statement here as an example. Let's say this is my conjecture. This is something which I believe to be true and I'm trying to prove it. 2 is the only even prime number below 30. Okay. Now here is a possible way of proving it. I could just write down all the prime numbers below 30, 2, 3, 5, 7, 11, and so on. You know the prime numbers below 30. And I could look at those numbers and I could say, well, that one is even, this one is odd, this one is odd, this one is odd, this one is odd. I could just look through the list and show that actually when I look at the list, they're all odd numbers. The only one that's even is 2, and that's my proof. Okay? And that has worked because I've looked at the list of all the prime numbers and I've considered each of them separately. So that is something that I can prove by exhaustion. There's only a few prime numbers below 30, I just look at each of them one at a time. Now if I cross off the below 30, then that doesn't work anymore. I can't look at the first million prime numbers and say, well, they're all odd apart from 2, because I've still got infinitely many prime numbers to look at. I can't look at the first billion because I've still got infinitely many prime numbers to look at. So I can't use that sort of idea if I'm just trying to prove 2 is the only even prime number. Okay, so now I need to use a proof by deduction. I need to say things like, well, an even number has to be in the 2 times table. If it's in the 2 times table, then it has a factor of 2. Therefore, it can't be a prime number unless it's 2. So therefore, 2 is the only even prime. So now I'm using a logical argument. I'm using facts that I know. I'm setting them out in a sensible order, like in section 7.4, a proof by deduction. Okay. But this proof by exhaustion is a very helpful tool in several cases. So first of all, if you know that there are only, if you need to prove something is true for all the numbers 1 to 100, one way of doing it will be proof by exhaustion. Okay, look, you've only got 100 cases to look at. Look at all of them. Now, in an exam context, perhaps that's a bit silly. We're not going to be able to do 100 different things. But if you were trying to prove an important mathematical fact and you've got it down to 100 cases, well, you could go through those one at a time. Okay. And the other way that we can use proof by exhaustion is the way that they're doing it here in example 12. Maybe we, so here we're trying to prove that all square numbers are a multiple of 4 or one more than a multiple of 4. Now this is all square numbers. I can't do this by looking at all square numbers. I can't write a list of all the square numbers and check whether they fit into one of these categories because there are infinitely many square numbers. But what I can do is I can split it up into odd numbers and even numbers. Okay? So there are now 2 cases to look at. If I prove the first case and I prove the second case, then I've dealt with it. Okay, and because the exam board are trying to teach you about proof by exhaustion, and they like you to be able to prove things that are sensible, not just say prove this is true for all numbers up to 10, for example. We often get this in the questions that they're asking us. If they're going to give us a proof by exhaustion question, it will often be something about all integers or all square numbers or all cube numbers or something like that, and the answer is often to look at even numbers and odd numbers. Not always, but you know, just be aware of it as a strategy. Okay, think split the thing that you're being asked to prove up into what about even numbers, what about odd numbers. So in this case, if we look at odd numbers, well, odd numbers can always be written as 2 times something plus 1, where the something is an even number. Where the something is an integer, right? So 2n plus 1. If I do 2n plus 1 and I square it, I get this, which I can factorize to this. So that is a multiple of 4 because n is a whole number, n plus 1 is a whole number. So I get a whole number times a whole number times 4, so that's a multiple of 4. And then I add 1, so that is 1 more than a multiple of 4. If I start with an even number, well, an even number can be written as 2 times n. 2 times n squared is 4 times n squared. 2 times n squared is 4 times n squared. N squared is an even number times by 4, so this is a multiple of 4. Okay, so all square odd numbers are 1 more than a multiple of 4. All even odd numbers are multiples of 4. And therefore, I can conclude all integers are either odd or even, so square numbers are either a multiple of 4 or 1 more than a multiple of 4, okay? So, proof by exhaustion, that's the idea. Either take all of the things you've been asked about, write them in a big long list and check them one at a time, or take all the things you've been asked about, split them into categories. In this case, even numbers and odd numbers. Consider the first category, consider the second category. Okay, and perhaps you can imagine if somebody's trying to prove something that nobody knows whether it's true, and we don't know, we're trying to prove a new mathematical fact. if you can't prove the whole thing, perhaps you can deal with the even numbers, and then somebody else later could come along and have a look at the odd numbers or something like that. And often, if you read about the history of maths, you find these examples where somebody proves a fact and proves that there's no exception below 1 billion, and then somebody else will come along and prove there's no exception below an even bigger number, and slowly we gather evidence, and eventually somebody manages to come up with a proof that proves our conjecture for all numbers. But there are often these little stages on the way, okay? Now, the next thing we get here is what we call proof by a counterexample. So if we have a fact and we don't know if it's true or not, okay? So here we go. The sum of two consecutive prime numbers is always even. So if you take two prime numbers, like 5 and 7, and you add them together, then what do we get? Well, 5 and 7 is 12, so that is an even number, okay? And if I keep checking that, I've got 11 and 3, and I add those two together, I get 14, and it's even, and I can spend a while adding together, consecutive prime numbers. We said consecutive, didn't we? So 11 and 13. So if we add those two together, we get 24, and that's even. So I could spend a while adding together consecutive prime numbers, and I could find that I'm getting even answers all the time. So I'm getting a lot of evidence that makes me think, well, maybe this is true. So my options are two things. One is try and prove that it's always true and try and come up with a reason. And the other option is to think, no, I think this is not true. And to prove that that statement is not true, all I need to do is find one example where it's not true, because the statement says the sum of two consecutive prime numbers is always even. So if I can find one place where the sum of two consecutive prime numbers is not even, then this statement can't be true because I can't say always, okay? And you've perhaps already worked out that the exception is where you have a 2, all right? So 2 plus 3 is 5. So that is two consecutive prime numbers. When I add them together, I don't get an even number. So this statement is not true, okay? But this is quite a good example because it gives us an insight into the way that maths works. I know that this is a sort of trivial statement and you can see through it, but think about how this would work if there's a mathematical fact and you weren't sure if it was true or not. You don't start by trying to construct a logical argument. You start by poking around and adding together some prime numbers and seeing what happens. When we do that, we get an even answer a lot of the time, and then this one particular time we get an odd answer. But by now, perhaps we can work out that actually we're getting an even answer because we're always doing an odd number plus an odd number with prime numbers. And we know that if you add together two odd numbers, you get an even number. And the only time that we have an even prime is 2. Okay, so maybe I can go back now and change my statement and say the sum of two consecutive prime numbers, both of them 3 or more, is always even. And now I can make my statement, I can construct my proof by deduction, can't I? I can say, well, I know that prime numbers are always odd, and the only exception is 2. 2 is the only even prime number. If 2 is the only even prime number, then if I add together any other prime numbers, I'm adding together two odd numbers. If I'm adding together odd numbers, I get an even answer. Therefore, if I add together two consecutive prime numbers, both of which are 3 or more, I'm going to get an even answer, okay? The conclusion that we're drawing there is kind of obvious, that the whole argument is kind of obvious, but it's an illustration of how careful we've got to be and the way that we might think through a more tricky puzzle. Start by experimenting, start by getting a feel for what you think is true. If you think this statement might not be true, then all you need is a counterexample. You need an example to show that it's not true. If you think the statement is true, then you need a proof. You might be able to do a proof by exhaustion, splitting up the statement into different categories and proving each of them separately. Or you might be able to do a proof by deduction, where you start with something you know to be true, you make a sequence of correct logical steps, and you end up with the statement, your conjecture, the thing which you are trying to prove. Okay? And in fact, they've called it jottings here. Look, so jottings, they've just made they've done a bit of scribbling about to try and work out what we're doing, and then they start their formal written proof. I'll leave you to have a look at example 14. So brilliant. That brings us to the end of chapter 7.